So the note then is, let's say you multiply matrix A, which has order m by n. So m rows, m is a counting number, n is a counting number, m rows by n columns. And B has order n by p, n and p are counting numbers, n rows and p columns. Notice that for the multiplication to be possible, these inner numbers have to match up. So you have the same number of corresponding entries so that you can take rows and times columns, right? And then the order of the product will be given by the outer numbers. So A times B as a product will have order m by p. If the inner numbers don't match up in the first place, just say the multiplication is undefined. Don't even try to do it. So we have matrix A with entries 1, -2, 0, -3. Matrix B, 3, 0, 4, -1, 5, 0. Find B times A. Let's analyze the orders. What's the order of B? What's the order of A? 2 by 2. What's the order of B? 2 by 3. So can we do B times A? So B, let's just analyze it right here. B, you told me, is 2 by 3. A is 2 by 2. What are you going to tell me when I say multiply B times A? Get lost. You can't do it, right? So undefined. We're going to look at whether or not we can do A times B. So now if we analyze the orders, A, like we said, is 2 by 2. B is 2 by 3. So that's supposed to be a 2 right there. Can you do it? The inner numbers match up. The number of columns in A matches up with the number of rows in B. That's what has to happen. So this is defined. So by the way, what does that tell you right away? Okay, every time you multiply real numbers A and B, doesn't matter if you take A times B or B times A, right? If these are real numbers. That's called the commutative property or commutative law of multiplication of real numbers. Is there a commutative a law of multiplication for matrices? No, it's not true. One of them's not even defined. The B times A isn't even defined. So some of the laws of algebra from real numbers hold, as we've seen. Some of them don't. This one doesn't. All right, you guys want to try this one on your own? See if you're awake? Try this one in your notes. Remember, to get any particular entry, you take row times column. What would the upper left-hand entry be? Give me the work that I showed in the last example. So just 3, would it be plus or minus 2? Plus 2. That's the upper left-hand entry, 5, right? Okay. So what would the middle entry be? So yeah, this guy times this guy, 0 minus 10, I think I heard. Is that what I heard? Yeah. Okay. Everybody see where that's coming from? Okay, what would the third entry in the first row be? 4 plus 0. That's the work you're going to have to show for the first row. You have to show it to get credit. And it's going to be on the final. Okay? No questions on that? Okay. What about the lower row? Oh, by the way, how did I know there were going to be 3 entries in the first row? Because if you look at the outer numbers, it's 2 by 3, so there's 3 columns, so 3 entries in the row. The number of columns gives you the entries in the rows, right? Okay, so now in your notes, hopefully you went down to the second row in the first matrix and then start over with the columns in the second matrix to get the entries in the product. So what do you get there? 0 plus 3. Okay, I buy that. And then what? 0 minus 15. All right. And then 0 plus 0. Okay, so finally, what? 5, negative 10, 4, 3, negative 15, and 0. Note, There is a multiplicative identity for an n by n matrix. N by n, we would call that a square matrix because it would have the same number of rows as columns, n rows by n columns. If it's we'll call it I for identity. If it's a 2 by 2 matrix, then it's the multiplicative identity is the matrix with zeros off the main diagonal from upper left to lower right and ones down the diagonal. And then if it's 3 by 3, you're going to have a diagonal with 3 entries and zeros off that main diagonal of ones. And then in general, if it's n by n, you just keep going. I don't know what n is, but if it's n by n, you just keep going down 1, 1, 1 in that stair-step pattern until you get n of them. And then you're going to have zeros off, off the main diagonal. And how many of them will be there, I don't know, so I'll just use a big 0. So ones down the main diagonal, zeros elsewhere. That's the multiplicative identity. Do you believe it? Let's try it. Let's take 1, 0, 0, 1. And let's just multiply it times a different matrix and see if we get the same matrix back again. So give me a matrix. Don't get too creative. 3, 2, 1, 2. Okay. So let's do the multiplication. We should be able to do it, right? Any square matrices, the inner numbers will match up. The number of columns in the first matrix will match up with the number of rows in the second matrix. So what happens when you multiply 1, 0, the row 1, 0, times the column 3, 1? That'll give you your upper left-hand entry. What will that give you? 3 plus 0, right? 0 times 1. Okay, let's go over here to get the second entry in the first row in the product. 1 times 2 is 2, plus 0 times 2 is 0. And you can see it happening, right? So you get 3 and 2, just like you're supposed to. And then to get the bottom row in the product, go to the bottom row of the first matrix and start over with the columns. 0 times 3, 1 times 1, will get you the 1. And then go to the next column, 0 times 2, plus 1 times 2. And you do get the matrix 3, 2, 1, 2, just like we wanted to get. So that at least if you multiply on the left, we didn't prove it if you multiplied on the right, but at least if you multiply on the left, you take the matrix 1, 0, 0, 1 times another 2 by 2 matrix, and you get that 2 by 2 matrix back again. That's the identity. That's what the identity does.